Hi guys, it's Dr. Bay and here's Bugsy, and today we're going to delve into substituted EAS reactions, so stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly fly, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
Electrophilic aromatic substitutions, or EAS reactions, are where one of the aromatic hydrogen atoms are replaced by an electrophile. There are a variety of new groups that can be installed on an aromatic ring, as shown here. But what if the benzene is already substituted? How does that affect the EAS reaction? Well, substituents on a benzene ring affect 1, the rate or speed of EAS, and 2, it affects the regioselectivity of EAS. Before we get into any of the details on this, let's first go over some aromatic substituent terminology. If you have a monosubstituted benzene ring with an R group as shown here, a second substituent that is installed 1 carbon away from the R group is called the ortho position. 2 carbons away, it's called the meta position, and 3 carbons away, it's called the para position. So this terminology will be super important for understanding directing group effects, so make sure you remember how to differentiate between each of the 3 positions around a benzene ring. Now recall when we learned about electron donating versus electron withdrawing groups. These groups actually have another name that they could be identified as. Electron donating groups can also be called activators, and they speed up EAS reactions. Some examples of strong activators are alkoxy groups, amino groups, and hydroxy groups. Weak activators that still fall under the electron donating group category are alkyl groups. On the other hand, electron withdrawing groups can also be called deactivators, and they slow down EAS reactions. Strong deactivators can be CF3, NO2, carbonyls, nitriles, sulfuric acid groups, or even ammonium groups. And weak deactivators are halogens. Now let's determine which is the fastest EAS substrate within each group. Remember that activators or electron donating groups speed up EAS reactions. So let's take a look at the first pair of molecules on the top left. A methyl group is considered to be an alkyl group, which is a weak activator. A CF3 group, on the other hand, is a strong deactivator. Since activators increase EAS rate, this substituent will be faster. In the next set of molecules, the dimethylamine group is a strong activator or electron donating group because the nitrogen atom directly connected to the benzene ring contains a lone pair of electrons that can be donated into the benzene ring. A methyl group, however, is still an activator, but it is a weaker activator than an amine. So the molecule on the left with the amine will be the faster EAS substrate. Now if we look at the group of molecules at the bottom, bromine is a weak deactivator, NO2 is a strong deactivator, and CF3 is a strong deactivator as well. Although all 3 are considered to be deactivators, bromine is the weakest deactivator, making it the fastest EAS substrate within this group of molecules. Now let's talk about the regioselectivity of EAS reactions and the directing effects that activators and deactivators have. All activators as well as halogens are considered to be ortho-para directors. Although both products are formed, typically the para position is favored slightly over the ortho position just due to sterics. In this general example, if you have any electron donating group connected to a benzene ring and undergo any EAS reaction, both the ortho and the para product will form, but the para product will just be more favorable. On the other hand, all deactivators except halogens are meta-directors. This means that if a benzene ring had an electron withdrawing group connected to it that then underwent an EAS reaction, the electrophile will add only to the meta position. So how do we identify the directing effects for the di and polysubstituted arenes or benzene rings? Well, let's look at this example of an aromatic halogenation with the following tri-substituted substrate. We know that this reaction should replace an aromatic hydrogen with a bromine atom, but we don't know exactly where the best position is to place that bromine atom. So to determine the most reactive position for an EAS reaction to occur, you're going to follow these 3 steps. In the first step, label each substituent in the reactant as either an activator or a deactivator, and also include their strength if you can too. In this example, a methyl group is a weak activator, a hydroxyl group is a strong activator, and a nitro group is a strong deactivator. In the second step, select the strongest activator, then identify its directing effects. Of these 3 substituents, the hydroxyl group is the strongest activator, and since OH is an ortho-para directing group, let's take note of where the ortho and para positions are with respect to the alcohol group. Now in the third step, we're going to identify the unoccupied sites to determine the most reactive position for EAS. Since one of the ortho positions is currently occupied by the methyl group and the one para position is already occupied by the nitro group, this means that the only vacant position is the other ortho position. This means that aromatic halogenation should only occur at this spot, the most reactive position. So the final product of this aromatic halogenation reaction shows that the bromine atom is ortho to the alcohol group. Let's do some more examples, starting with the reaction in the upper left-hand corner. The following reactant is undergoing nitration, so first let's label the substituents. A hydroxyl group is a strong activator, and a methyl group is a weak activator. Since hydroxyl is a stronger activator, it will be our reference point for directing effects. Because the para position to the alcohol group is already occupied, that means that the nitro group can only add to either ortho position to get the following product. In the next example, the following reactant is undergoing Friedel-Crafts alkylation. Since both substituents are methyl groups which are of equal strength to one another, it doesn't matter which methyl group we choose as our reference point. Let's just pick the right methyl group for this example. Notice that all 3 positions are unoccupied, the 2 ortho positions as well as the 1 para position. We do not want to place the methyl group in between the 2 existing methyl groups due to sterics. So we will place it on the other ortho position to reduce steric interactions between all 3 groups. If you chose to place it at the para position to this methyl group, you would get the same product. In the next example, then we have to compare a tert-butyl group versus a methyl group. Since they are both alkyl groups of equal strength, we're going to look at bulkiness. This reactant is undergoing aromatic halogenation, and we're going to choose the smaller alkyl group to be our reference point to avoid steric interactions. Since methyl is our reference, notice that the para position is already occupied by the tert-butyl group, so this means that the bromine atom can only add to either of the ortho positions with respect to the methyl group to get the following product. And in the last example, a tetrasubstituted arene is undergoing an aromatic halogenation. So let's label all 4 substituents. The ketone up at the top is a strong deactivator. The bromine atom is a weak deactivator. The dimethylamine group is a strong activator. And the methyl group is a weak activator. Of these 4 substituents, dimethylamine is the strongest activator, so it will be our reference point for the halogenation reaction. Notice that both ortho groups are already occupied with respect to the amine, so the only position for chlorine to add to is the para position to get the following product. So, in summary, electron donating groups can also be called activators, which speed up EAS reactions. All activators, as well as halogens, are ortho-para directors. Conversely, electron withdrawing groups can also be called deactivators, which slow down EAS reactions. All deactivators except halogens are meta-directors.
Organic.